Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, welcome back. For each week of the course, there's going to be a separate tutorial to review the homework problems. So let's get started on problem 1 for week 1. Problem 1 just asked you to calculate the force between two sodium ions that are separated by a distance z. We want this force to be 1 nanonewton, and we want to find out the separation z that's required for this 1 nanonewton force. The force is repulsive because the sodium ions are both positively charged. We're not terribly interested in whether the force is attractive or repulsive. We just want the magnitude of the force. The charge associated with each sodium ion is the charge that remains after 1 electron has been removed. So the charges in this problem are both equal to 1.6 times 10 to the minus 19 coulombs, which is the magnitude of the charge on an electron. If we were going to calculate this force in free space, we would just use Coulomb's law because these are, to a very good approximation, point charges. So the force due to Coulomb's law is proportional to the product of the two charges, Q1 and Q2. It's inversely proportional to the distance z squared. The proportionality constant is this 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. So in this problem, the forces are in newtons, the charges are in coulombs, and the separations are in meters. Now the problem is a little bit different because it's stated in the statement of the problem that these ions are embedded in a dielectric. Right, so there's a uniform dielectric that fills all space between the ions, and it's stated that that dielectric constant is 24. So that comes into this problem simply as a factor 1 over kappa. So kappa actually, the dielectric actually will reduce the force of the repulsive force between these two ions. So we're asked to solve for z such that the force F is 1 nanonewton. So what we have to do is we have to solve this equation for z, right? So z squared is going to be 1 over 4 pi epsilon naught times 1 over kappa times Q1, Q2 divided by the force F. We can now evaluate these quantities, right? So we have z squared is equal to 1 over 4 pi. Epsilon naught is a well-known constant. It's 8.85 times 10 to the minus 12. And the units are coulombs per Newton meter squared. All right, so that's the first term. The charges are the same, so it's 1.6 times 10 to the minus 19 coulombs. That has to be squared. And the force is 1 nanonewton, so it's 1 times 10 to the minus 9 newtons. It's easy to solve this this equation for z, and when I do that, I get that z is equal to 98 picometers, which is 98 times 10 to the minus 12 meters. So the correct answer for question 1, part 1, is C. Okay? Now, the second part of the problem just asks what is the electrostatic potential energy that develops when these two charges are positioned one from another by this 98 picometers. Again, if the two charges were located in free space, The electrostatic potential energy for two charges is 1 over 4 pi epsilon naught, Q1, Q2 divided by Z, the separation distance. U is a sign quantity, and the sign of this quantity is going to depend on the product of the signs of the charges Q1 and Q2. So in this case, Q1 and Q2 are positive, so that means that the electrostatic potential energy is going to be a positive number, which just simply means that it's going to require work for you to push these two charges to this final separation of 98 picometers. Again, the same condition applies because we have a dielectric constant of 1 over 24. We have to insert that into the problem. Of course, that also has to be inserted into this problem here. I left it out, so there's a 1 over 24. Okay? So all the constants are given. The distance Z is 98 picometers. When I evaluate this expression, I get an answer which is plus 9.8 times 10 to the minus 20 joules. And so if I look at the choices, the correct answer is B. That's the correct answer for the second part of problem 1. The third part of problem 1 asks you to calculate the thermal energies and compare the thermal energies to the electrostatic potential energy that's present. So what we're trying to do here is we're trying to get a feel for whether the electrostatic potential energies are going to dominate or the thermal energies are going to dominate in this particular problem. So to a very good approximation, the thermal energy is just equal to the Boltzmann's constant K sub B times the temperature T. Temperature T has to be in degrees Kelvin. So we're going to choose 300 Kelvin. That's very close to room temperature for this estimate. Boltzmann's constant is a fundamental constant that's well known. Its value is 1.38 times 10 to the minus 23 joules per Kelvin. So to evaluate the thermal energy, I just have to multiply these two quantities together. And when I do that, I get about 4.1 times 10 to the minus 21 joules. So now we can form the ratio of the electrostatic potential energy to the thermal. So right, so it's 9.8 times 10 to the minus 20 joules divided by 4.1 times 10 to the minus 21 joules. And that number is on the order of 24 when you work out that arithmetic. So this just means that the electrostatic potential energy of interaction is about 24 times the thermal energies available. And it just gives you an indication that when these two charges are this close together, right, the electrostatics is going to win over the thermal energies. As the separation between the two charges increases, of course, this thermal energy will remain fixed. The electrostatic potential energy will decrease as 1 over Z, and eventually electrostatics and thermal energies will become comparable one with respect to another. So the correct answer for the third part of question 1 is going to be C. The thermal energies are too small to overcome the electrostatic energy required for the specified configuration. So that's the solution for problem 1.